Beyond the Milky Way lies a colossal neighbour, the Andromeda Galaxy, moving silently toward us through the dark. Tonight we begin a calm voyage across that endless distance to uncover its hidden wonders. If you enjoy this journey, please like, subscribe and share, and tell us in the comments, what would you do if you could travel to another galaxy? Thank you for watching. Now let's begin. The view opens on a quiet sky that seems simple and near, yet every point of light holds a distance that stretches the sense of scale. The universe presents a background that is smooth on the largest reaches and richly textured on smaller spans, a web of filaments and nodes separated by deep voids. This woven structure forms over billions of years as matter drifts under gravity, and within that web rests a modest assembly of galaxies that observers call the local group. The Andromeda Galaxy belongs to this assembly, and its future is bound to the currents running through this wider network. It rests not alone, but within a filament that channels dwarfs gas and star clusters, a thread that continues beyond sight and bends according to the mass around it. The cosmic microwave background, a faint glow that fills the sky in all directions, sets the uniform backdrop for this structure, yet the smoothness of that glow is not the whole story. Slight variations guide the growth of clusters and sheets, and over time these small seeds bring forth immense forms. Against this background, the local group appears as a relatively small neighbourhood, but even a small neighbourhood in cosmic terms spans millions of light years and contains hundreds of billions of stars. Andromeda and the Milky Way are the two great anchors of this neighbourhood. Each carries a retinue of satellite galaxies, clouds of gas and extensive dark halos that reach far beyond the light of their disks. The space between these two anchors is not empty. It holds thin streams of stars, tenuous gas, and the gravity field that shapes the future path of both systems. To frame Andromeda within this expanse, orientation matters. Observers map sky coordinates to a three-dimensional grid, then translate motions measured on the sky into motions through space. The process begins with careful reference frames tied to distant quasars whose relative stillness sets a stable backdrop. On this foundation, apparent drifts of galaxies are converted into velocities, and those velocities are related to the larger flow of matter along the filament that threads the local group. When this framework is laid out, Andromeda's place becomes clearer. It stands a little more than 2 million light-years from the Milky Way, set slightly above the plane that contains the primary stream of nearby dwarfs. Its disk tilts at a modest angle to our line of sight, so spiral arms and dust lanes overlap from our viewpoint. The halo surrounding the luminous disk extends many times farther than the light, blending into the dark matter envelope, whose gravity organizes the motion of satellites. Beyond the local group, the cosmic web continues toward a nearby concentration of mass that researchers call the Virgo cluster. The local group does not fall directly into that cluster today, but the general tug from that direction adds a slow drift to the motion of our neighbourhood, while smaller scale pulls within the local group govern the near future. Through this multi-layered pattern of forces, Andromeda moves along a path that appears simple when projected on the sky, yet is shaped by many contributions. The galaxy's light arrives as a blend of ancient stars from the halo, intermediate age stars in the disk, and vigorous young stars in regions of current formation. These populations speak of a history of steady growth, punctuated by events that leave subtle marks in structure and motion. The stars we see today illuminate only a fraction of the mass that sets the rhythm of Andromeda's travel. The rest lies in a dark envelope that does not shine yet reveals itself through the speed of stars and satellites. The local group is more than a passive setting for this motion. It is a dynamic environment that gathers small galaxies along preferred directions and feeds them into the potential wells of the larger systems. Some dwarfs orbit for long periods, shedding streams of stars that trace their paths like pale ribbons. Others plunge on nearly radial tracks and dissolve in a few passes, adding their material to the disk or halo. These processes fill the outskirts with faint structures, and together they hint at the long record of interactions that bring the present form into being. To hold this panorama steady in the mind, a sense of scale is essential. The distance between Andromeda and the Milky Way is measured in millions of light-years, a stretch so wide that light, the fastest messenger known, takes more than 2 million years to cross it. Within Andromeda's disk, typical separations between major spiral arms reach thousands of light-years. Star-forming clouds span dozens to hundreds of light-years. Individual stars like the Sun are a fraction of a light-year apart from their nearest neighbours. Every level of this hierarchy fits within the next, and the whole structure drifts calmly against the deeper background of the universe. The stillness is only apparent. Over tens of millions of years, the motion becomes visible through changes in position and velocity, and over billions of years that motion leads to close passages and eventual unions. The local group sits at the edge of a larger sheet of galaxies that stretches across tens of millions of light-years. This sheet bends around voids where few galaxies form, and along the edges of these voids the density rises enough to gather new members. The Andromeda galaxy moves within this field, its path guided by the mass of its own halo, by the pull of the Milky Way, and by the cumulative draw of the nearby sheet. The combined effect is a slow approach that has already begun. Astronomers measure this approach by comparing the spectrum of Andromeda's light with the known patterns of atomic emission and absorption, and by tracking minute shifts in position relative to faraway reference points. These methods do more than predict a meeting. They reveal the complexity of the space through which the galaxy moves. Even the faint gas that threads the web can exert gentle pressure over long times, and the wake of smaller galaxies can leave imprints in the outskirts of Andromeda's disk. The framing of the cosmic horizon therefore serves two purposes. It gives context for what Andromeda is now, and it sets the stage for how its form will evolve. The galaxy is not an isolated island, but a city within a continent of structures connected by roads that are made of gravity and time. The background that looked smooth at first becomes a map of pathways. The voids are the quiet districts. The filaments are the thoroughfares along which matter streams. The nodes where filaments meet are the crowded intersections that host rich clusters. The local group resides on a side street of this network, quiet but not deserted, and along that street Andromeda glides with patient momentum. Within this framing, the mind can hold both the immensity of the setting and the specific features that define Andromeda's identity. It has a luminous disk with spiral geometry, a halo that stretches far into near emptiness, a suite of companions that trace its gravity, and a forward path that points toward a future encounter. Each of these elements will unfold in the sections ahead, but the wide horizon remains present as a quiet boundary that reminds the narrative of its scale. Andromeda's voyage is not a sprint or a straight line. It is a long drift across a web that formed from the faintest ripples in an ancient glow, a measured progression where every small motion feeds into a larger pattern that only becomes clear when viewed across deep time. In this first view, the universe offers stillness that is not truly still order, that is not entirely smooth, and a path that is both gentle and inevitable. The Andromeda galaxy rests within that calm tension, balance between the serenity of the present and the pull of what lies ahead. The story of Andromeda in human awareness begins long before telescopes, when careful watchers of the night sky map familiar patterns for navigation, timekeeping and ceremony, and when a soft oval patch near a chain of stars becomes a steady mark in seasonal memory. Ancient catalogues fix the brightest stars and note a few hazy objects, yet the pale glow in Andromeda remains a quiet curiosity, a gentle cloud that does not change from night to night. As glass and craft improve, the first small telescopes gather enough light to show that the haze is not a single star but a luminous smear with a brighter centre, and the simple act of magnification turns a guess into a question. What kind of thing makes light that spreads rather than points, and how far away must it be to appear as a little cloud to the eye? During the era of careful sky sweepers who search for comets, the object is listed among other diffuse lights, so that seekers will not chase a false visitor, and this practical impulse becomes the first step toward a clearer identity. Drawings in the 19th century show an elliptical glow with a condensed core, and long exposures on glass plates reveal faint extensions that the eye cannot hold. Photographic emulsions accumulate light over hours, and the luminous blur stretches into a soft spindle with hints of swept structure. The photograph becomes a new sense, one that remembers every photon and keeps stillness beyond the patience of the human hand. Spectroscopes added to telescopes separate the light and show that the glow contains the fingerprints of stars rather than the continuous sheen of a cloud of gas alone, and this result tips the balance toward a stellar system of some kind. Yet the mind of the time faces a decision. Either the universe is a single city of stars and these spirals are small structures inside it, or the universe is a country filled with many island cities that lie far beyond the main streets of the known stellar map. In the early 20th century, novas recorded in the Andromeda glow appear much fainter than novas inside the Milky Way, and their distribution in the oval light confuses easy categorization. Some observers note that if these bursts are the same kind of event as those nearby, the distance must be vast. Others argue that the nature of the bursts may differ, and so the object may still lie within the known stellar city. Debates gather careful reasoning on both sides, and each new plate, each measured spectrum adds weight but does not end the argument. Meanwhile, mapping of stellar positions within the Milky Way proceeds with growing sophistication, and a pattern emerges that hints at spiral structure within our own system, a hint that shapes the way observers interpret spirals seen beyond. The question of distance remains the key, and to answer it requires a kind of star that can serve as a reliable beacon. Variable stars that change brightness with a rhythm tied to their true power provide such a measure because once the rhythm is known, the intrinsic light can be inferred, and from the observed faintness the distance can be computed. The search for these stars in Andromeda asks for clear resolution of individual points within a sea of light, and it demands a large telescope, sharp plates and patience over many nights. When the pulses of these stars are finally traced, and the periods read, the numbers yield a distance that reaches far beyond the scale of the Milky Way, as it was then understood, and a boundary in thought swings outward. The diffuse oval is not a local cloud, but another stellar city, a galaxy with a starry population of its own. With distance in hand, the implications cascade. The size of the object grows from a few hundred light-years to tens of thousands of light-years and more. The luminosity rises from a handful of suns to hundreds of billions of suns. The Andromeda galaxy becomes the nearest large neighbour, a peer rather than a subordinate, and the universe becomes a realm rich in such peers scattered across space. Photography continues to refine the portrait. Longer exposures uncover dust lanes that cross the bright central regions and trace dark curves through the arms. Star-forming knots sparkle, and the outer glow deepens into a broad disk. Metal lines in the spectrum sketch the mix of elements in the stellar populations and comparisons, with populations inside the Milky Way hint at both shared processes and local histories. Radio observations add the cool voice of atomic hydrogen, drawing a map of gas that extends beyond the bright stars and shows where spiral arms carry reservoirs for future starbirth. Measurements of line, shifts from one side of the disk to the other, reveal rotation a pattern of motion, where the inner regions spin swiftly, and the outer regions do not slow as much as simple expectations would predict a clue that points toward mass beyond visible light. Even before the modern era of space telescopes, careful plates and radio maps suggest that the luminous portion is only the central embroidery on a much larger invisible fabric. The human chain that carries understanding from the first naked eye impression to these intricate pictures is long and patient. It runs through workshops that grind lenses and polish mirrors, through observatories built on dry peaks, through nights of steady attention, where a thin line of ink marks the timing of a star that grows brighter and fainter, with a locked rhythm, through dark rooms where silver crystals respond to photons as faithfully as rain gauges collect water, through notebooks where numbers climb into columns and turn into distances. Each advance invites a new puzzle. The early drawings show a shape that looks simple and symmetrical, but deeper photographs reveal asymmetries in brightness and structure. Spectra show the light of stars, yet also show gas that absorbs and re-emits, signing its presence in the path. Novas appear in numbers that force a reconsideration of how often stars reach outbursts in crowded fields. The rotation pattern implies mass beyond what the light can account for, sketching the first outlines of a dark halo not yet named as such. By the middle of the 20th century, the object that was once a modest blur becomes the foundation for a new sense of scale. Galaxies fill the sky out to distances that are counted in hundreds of millions and billions of light years, and the local group takes on a meaning as a neighborhood rather than as the whole of creation. Within that neighborhood, Andromeda becomes a benchmark for methods that will be applied to thousands of others. Distances anchored by variable stars are extended by other rungs on a ladder that reaches farther outward, and the refinement of those rungs often begins with tests in Andromeda, because it is near enough to resolve yet far enough to be an external system. The path from first sight to measured distance to detailed structure is not a rush, but a slow unfurling. The patience of observers mirrors the patience of the galaxy itself, as it turns on timescales longer than any human life. Each generation receives a clearer image and a longer baseline of measurements, and with each addition the narrative rebalances. The object in Andromeda shifts from wonder to measurement without losing wonder. It is still a cloud to the eye on a dark autumn night, and it is also a grand island of stars whose distance has been read from the beat of tiny beacons, and whose mass has been weighed by the falling of light and the speed of motion. The early era leaves the present with a lesson that continues to guide discovery. The sky gives up its meaning slowly, and each method sees only a part of the whole. When different senses are brought together, the picture becomes more trustworthy and more complex at once. Andromeda steps forward in this way, from a haze to a galaxy, from a simple mark on a chart to a central figure in a broader map, and it carries with it the questions that new clarity always brings. Modern maps of the local group grow from a patient braid of measurements that turn the sky from a flat pattern into a living structure with depth, motion, and history. Space observatories, ground-based telescopes on dry mountain summits, and radio dishes that listen to cold gas, all contribute threads that are woven together until positions, distances, and motions relate to one another in a shared frame. The European mission named Gaia measures the tiny shifts in star positions that occur as Earth moves around the Sun and as stars move through space, turning minuscule angles into true distances and sideways motions for millions of stars. In the halos and disks of the Milky Way and of the Andromeda Galaxy, these measurements trace swathes of stellar orbits and allow astronomers to place individual traces on a three-dimensional map rather than on a simple plane. The Hubble Space Telescope and its successors reach out to the satellite galaxies and bright star-forming regions within Andromeda, resolving variable stars and the sharp cut-offs of red giant branches that act as distance rulers. Ground-based surveys sweep the sky with wide cameras counting red giants and horizontal branch stars that stand out in color space, and in this way the faint outskirts and tidal plumes become visible. Radio arrays follow the whisper of atomic hydrogen, a line that reveals where cold gas gathers along spiral arms, warps into flares at the edge of disks and streams through the intergalactic medium like gentle rivers between larger shores. Infrared instruments pierce dust and bring cool stars and young clusters into the map, while ultraviolet observatories highlight the most recent starbirth. Each of these senses sees a different layer of the same landscape. When they are combined, the local group becomes a volume with river shells and bridges rather than a set of separate shapes. With distances in hand, membership can be defined more clearly. A dwarf galaxy that sits within a certain radius, where the pull of the Milky Way or Andromeda outweighs the general expansion of the universe, can be said to reside in that primary halo. A dwarf beyond that radius, but still inside the wider boundary, where the local group remains a coherent entity, can be considered a member of the local group. The map shows chains of dwarfs that line up along thin planes or inclined sheets, patterns that may reflect the directions from which material fell in during the last few billion years. Some of these planes point back along the filament that links the local group to nearby associations of galaxies. Others may mark the remnants of past groups that entered together and were stretched by tides. By counting satellites and weighing their motions, astronomers infer how much dark matter sits in the halos of the two primary galaxies and in the shared envelope that embraces them both. Proper motions add the third component of velocity that line-of-sight measurements alone cannot provide. The Andromeda Galaxy shows a small drift on the sky, relative to background quasars, a drift measured over years with the precision of space-based imaging. When this sideways motion is combined with the approach speed that has long been measured from the soft pull of spectral lines, a full vector emerges. That vector is then placed into a frame that accounts for the Sun's path around the Milky Way, and for the Milky Way's own motion within the local group. The result is a clearer prediction of the dance that lies ahead. The approach is slow on human timescales measured in hundreds of kilometers per second, but across billions of years such a pace closes the gap. Yet the map is not a simple arrow from one large disk to another. It is a web of streams that record past passages of smaller galaxies. In the outskirts of Andromeda, star counts reveal long cold arcs of debris that wrap around the galaxy like faint ribbons of frost. These are the unspooled remains of satellites that ventured too close and were pulled apart. Their paths mark the mass distribution of the halo, because only certain orbits produce the measured wraps, and only certain total masses allow the stars to be where they are now. In some cases, coherent star clusters ride along these streams, serving as bright knots that can be traced across the sky. Globular clusters spread through the Andromeda halo in numbers larger than those found around the Milky Way, and their velocities offer a separate path to the same gravitational truth. By combining the motions of clusters, streams, and halo stars, astronomers shape a gravitational portrait of the galaxy and of the wider local group. The intergalactic medium between the Milky Way and Andromeda is faint but not empty. Absorption lines seen in the spectra of distant quasars reveal that thin gas lies along certain lines of sight, some of it enriched by the past activity of stars, some of it nearly pristine. These strands of gas do not shine strongly, but they may feed both large disks over time, and their distribution shapes how star formation waxes and wanes in the outer regions. Modern maps also reveal that the outer disks of both major galaxies are not flat. The Andromeda disk shows a warp that lifts one side and dips the other, a gentle tilt that likely remembers a past encounter with a dwarf or the continuing pull of a massive companion. Radio maps of atomic hydrogen trace this warp more clearly than starlight does, because gas responds quickly to tidal nudges and settles slowly. The geometry of this warp becomes another constraint on the mass and past paths of satellites. Membership lists of the local group change as deeper surveys expose fainter dwarfs, and as motions refine positions in 3 dimensions. Ultra-faint dwarfs with a few thousand stars come into view, some barely held together against tidal forces, some already in the act of dissolving into streams. The spatial distribution of these tiny systems around Andromeda and around the Milky Way is not perfectly even. Some sectors show richer gatherings, others show gaps, and these patterns speak to the anisotropic nature of accretion along filaments. The map is therefore both a static picture of where stars are now and a dynamic diagram of how material flowed in. A core question that modern mapping addresses is the total mass of the local group and the division of that mass between its 2 giants. One approach uses the timing argument, which treats the Milky Way and Andromeda as a pair that pulled away with the general cosmic expansion and then slowed and turned toward one another under mutual gravity. The present separation and relative velocity combined with the age of the universe, as inferred from the cosmic microwave background and other measurements, suggest a total mass that must be shared between the 2 halos and their extended envelopes. Another approach uses the motions of satellites as test particles within these fields, while a third uses the shapes and speeds of stellar streams. No single method is final, but together they converge on a mass sufficient to explain the observed motions and to sustain the long reach of the halos. Modern maps are not drawn once and finished. They are living documents revised with each new data release. A faint set of stars once thought to be smooth background may resolve into a stream. A dwarf suspected of belonging to Andromeda may prove to be more distant and instead belong to the outer rim of the local group. A cluster thought to be isolated may be found to ride a filament of debris. Through this continuous revision, confidence grows not because uncertainty vanishes, but because multiple senses point to the same underlying structure. Andromeda stands in these maps as a dominant city within a county of smaller towns, surrounded by roads of stars and gas that lead inward from the countryside. Its satellites feel its pull, and that of the Milky Way and some trace orbits that carry them through the shared borderland where allegiance shifts. With each refinement, the local group looks less like a scatter of points, and more like a weather system with flows, eddies, and fronts. In this weather, Andromeda is a high-pressure centre, with long arms, a quiet whirl whose winds are stars, and whose memory is written in the shape of its outskirts. The map that reveals this is both a tool and an evolving story, one that prepares the mind to follow specific structures inward in the sections to come. The outermost regions of the Andromeda galaxy fade beyond the reach of ordinary starlight, yet continue as a vast halo whose gravity holds sway long after the bright disk ends, and this unseen reach reveals itself through the motions it imposes on stars, gas clusters, and small companion galaxies. Astronomers weigh this dark envelope by following test particles that move under its pull-turning speed and position into a map of mass that does not shine. Atomic hydrogen in the outskirts traces a rotation curve that stays high even where starlight thins to near invisibility, a sign that matter remains abundant though it refuses to glow. Satellite galaxies orbit within this extended field and serve as wandering markers whose velocities, when combined with their distances and directions of travel, sketch the depth of the halo. Globular clusters provide another set of beacons old and bright enough to track far from the centre, and their speeds show that the gravitational hand remains firm at radii, many times larger than the luminous disk. Streams of stars, the long ribbons pulled from disrupted companions, also act as rulers because their shapes and dispersions depend on the mass they have moved through. To fit all of these traces at once, researchers build models with mass that rises gently from the inner bulge through the disk and into a spherical or slightly flattened halo that stretches for hundreds of thousands of light years. In these models, the halo contains most of the total mass, and the luminous parts ride like a thin crust on a deep sea. Evidence beyond motion adds weight to this picture. A warm bath of gas surrounds Andromeda, thin and hot, detected through the way it absorbs and emits light at ultraviolet and X-ray wavelengths, and this circumgalactic medium holds heavy elements that must have been cast outward by earlier generations of stars. The pressure and extent of this gas are consistent with confinement by a deep gravitational well, and the way cool clouds fall and mix within this medium points to a halo that is both massive and structured. Farther out, the weak bending of light from distant background galaxies offers a direct touch of gravity known as weak lensing, and statistical measurements of the slight alignments in those background shapes around Andromeda strengthen the case for a broad, massive halo. Yet the dark matter itself stays hidden, except for its pull. It is not a gas that cools and sinks, not a star that burns, not dust that reddens light. It is a component that carries mass without light, and its distribution tells a history of slow assembly and punctuated growth through mergers. The outer halo is therefore both archive and boundary. It records the arrival of smaller systems along preferred directions, and it sets the limits within which the present-day disk and bulge can remain stable. The warp of the outer gas layer, which lifts one side of the disk and dips the other, likely remembers a recent nudge from a companion that passed through the halo, while the continued coherence of certain stellar streams implies that the overall gravitational field is smooth on large scales, with only gentle lumps where dark subhalos may wander. The total mass inferred from these lines of evidence reaches well beyond what stars and cold gas can supply. When the motions of satellites are treated as a population within a central field, their velocity spread demands a halo mass of several times 10 to the 12th suns. Though precise values carry uncertainties that reflect limited sample sizes and the unknown shapes of some orbits. Rotation curves add complementary constraints inside the outermost reaches, while the timing argument that considers the approach of Andromeda and the Milky Way together offers a shared mass for the pair and their common envelope. By balancing these methods, astronomers arrive at a portrait in which the Andromeda halo is at least as massive as that of the Milky Way, and maybe somewhat larger, a conclusion that aligns with the richer population of globular clusters and the more pronounced system of stellar streams seen around Andromeda. The shape of the halo matters as much as its mass. A perfectly spherical halo would steer satellites and streams differently from a slightly flattened or triaxial one, and careful fits to the paths of known streams suggest modest departures from roundness. The degree of flattening also influences how gas accretes where warps persist, and how the disk maintains its thickness. In simulations that grow galaxies from early fluctuations in matter, density halos settle into shapes that are close to spherical in the outer parts, and become more flattened where the luminous disk is dominant, and Andromeda appears to mirror this general behavior while displaying its own local quirks. Those quirks include asymmetries between opposite sides of the halo, where star counts in the outskirts rise on one side and fall on the other, and where stream density and globular cluster orbits prefer certain sectors. Such asymmetries may record the recent infall of a dwarf group along a filament, or the long aftermath of a past major interaction, whose debris still rains down in measured arcs. The halo also governs escape. There is a speed above which a star or a cluster will not be bound to Andromeda, and by measuring the fastest halo stars and the most extended cluster orbits, astronomers estimate that escape requires hundreds of kilometers per second, even very far from the center. This threshold helps fix the outer mass and sets expectations for how much debris will remain within the system after close passages with the Milky Way begin. The hot gas that fills the halo cools slowly, but where cold clouds condense and fall, they may light brief star formation in the extreme outskirts, and the balance between heating from stellar activity and cooling through radiation may vary with radius. The presence of metals in the halo gas shows that winds and fountains driven by star formation and by the central region have carried processed material outward, yet the faintness of the medium reveals that most mass in the outer parts is not gas but dark matter. The nature of this dark matter remains an open question. Particle candidates must be slow moving enough to clump on galaxy scales, or else the fine substructure traced by streams and dwarfs would be washed away. On the other hand, if dark matter were made of compact objects like faint black holes or cold remnants, lensing events and dynamical heating would likely be stronger and more frequent than observed. Alternatives that modify gravity rather than add unseen mass must also reproduce the combined pattern of rotation, curves, satellite motions, lensing signals, and the growth of large-scale structure, a high bar that many find difficult to clear across all data sets at once. In this tension between elegant possibilities and stubborn measurements, the Andromeda halo stands as a testbed. Future passes of precision astrometry will refine the sideways motions of more halo stars and clusters. New spectroscopy will enlarge the sample of fast tracers, and deeper imaging will pull more streams from the background. Each addition will tighten the portrait of the halo's mass shape and history. Still, mystery is not removed, only reduced in size, because the very existence of a massive invisible component remains an unanswered invitation. The outer halo of Andromeda, silent and vast, holds the keys to how the galaxy grew, how it stabilizes its luminous parts, how it gathers and sheds material, and how it will meet and merge with the Milky Way. It is the soft edge that is not soft at all, the dark ocean that carries the bright island and decides where its shores can be. By looking outward first and by letting gravity speak where light refuses the narrative, learns to read the deepest layer of the galaxy's architecture before stepping inward to the places where stars blaze and dust sculpts arms, and where the hidden mass continues to guide from the shadows. The cold streams in the halo of the Andromeda galaxy form when small galaxies and loose star clusters fall inward and are pulled apart, leaving long ribbons and layered shells that mark their paths like frost traced by a steady wind, and in these fragile patterns the past becomes visible. Deep wide-field imaging selects the cool light of old red giant branch stars and teases them from the dense foreground of the Milky Way. And once the subtraction is done, thin structures rise from the noise and thread the outskirts in arcs, loops, and broken swaths. Spectroscopy then assigns each star a motion along the line of sight, while careful measurement of color and brightness fixes an approximate distance, and together these senses lift the stream off the flat sky and place it in three-dimensional space. Some features draw near the luminous disk and then swing far out into the halo, before returning a sign that their orbits are long and eccentric, and that the parent system's plunged close to the center, where tidal forces are strongest. In several quadrants, shells appear, piled like the edges of ripples where a stone has struck a pond, and these shells fit naturally when a compact dwarf galaxy makes a near head-on pass and sheds stars at different speeds, so that the faster group runs ahead and piles up at one radius, while slower layers catch up later to form another. The metal content of these streams read from the way stars distribute along the red giant branch and from absorption lines in their spectra, varies from one feature to another, and reveals that the falling companions range from poor dwarfs with simple histories to richer systems that formed stars over longer periods and carried heavier elements into the halo. The most luminous of the streams carries stars that are older than most of those in the disk, yet younger than the ancient halo field, and this mix points to a satellite that grew quietly for a time before its capture. Globular clusters that move along with certain streams act as bright flags that can be traced farther than diffuse starlight alone, and where a cluster shares the chemistry and motion of a stream, it likely rode within the host dwarf and was released when tides unstitched the parent. The shape of a stream is a timepiece. A tightly wrapped arc close to the galaxy hints at a recent pass, while a diffuse band stretched across a large sector suggests an older event that has had time to disperse. The width of a stream reflects both the mass of the parent and the grain of the gravitational field, for a grainy field filled with dark subhalos would stir and thicken the ribbon more than a smooth one. In Andromeda, many features retain surprising coherence over long spans, implying that the large-scale halo is smooth, and that the population of heavy dark clumps is not so large as to erase the record quickly. Yet not all lines are thin, and in places the strands show kinks and forks, perhaps where a passing substructure or a previous wrap perturbed the path. Phase mixing, the slow spreading of stars along an orbit, as small differences in speed accumulate steadily, turns sharp features soft, and this gentle blur allows approximate ages for an encounter to be inferred when the geometry and motion are known. The ensemble of streams sketches the total mass and the shape of the halo, because only certain distributions of mass allow the observed paths and speeds to coexist, and so modelers launch test particles through candidate gravitational fields until the simulated ribbons lie where the sky shows them. In some sectors, the density of streams and shells is higher, and that imbalance hints that accretion has been directional, with a recent supply of dwarfs arriving along a particular filament of the larger web. A narrow plane of orbiting companions extends on one side and carries several streams with similar orientations, a geometry that may record the infall of a small group that was once bound and is now unspooling member by member. Farther out, faint bridges of stars and gas link the halo to more isolated companions, and where those bridges narrow and break, they seed new streams that will brighten as they cross denser fields. Radial velocities along a single feature often change smoothly from one end to the other, and that gradient reveals whether the stars are moving toward the center, on the near side of the orbit, or curling away on the far side, and in this way the three-dimensional loop is reconstructed from a two-dimensional projection. In a few places, streams pass behind the outer disk and their stars dim under dust lanes before reappearing beyond, and this interruption offers a chance to measure how dust is arranged in the outskirts, while also testing the continuity of the ribbon. The presence of streams near the outer disk also feeds the warp, because a passing dwarf can torque the gas, and lift one side while lowering the other, and a robust stream crossing at a shallow angle can leave a line of star formation where gas is stirred. The shells nearer the center mark deeper plunges, where the parent loses mass quickly, and their sharp edges act as a ruler for the central potential, since the pile-up occurs where orbits turn under the same gravitational law that governs the bulge and inner halo. The streams carry not only positions and velocities but also a fossil chemistry. Stars born in a small dwarf carry fewer heavy elements than those born in a larger system, with cycles of gas inflow and supernova winds, and so a metal-poor ribbon likely came from a light parent, while a metal-rich arc suggests a heavier dwarf that may have hosted clusters and prolonged star formation. By comparing the chemistry of a stream with that of nearby halo stars that do not follow the ribbon, one can measure how the smooth halo has been built from many past events that are now fully mixed while the stream remains a recent chapter not yet folded into the general field. The rate at which streams are discovered increases as surveys deepen, and as algorithms learn to find subtle coherence in position, motion, and colour all at once, and each new feature extends a timeline of the halo's growth. Some streams show tentative evidence of young or intermediate age stars, which would mean that the parent was still forming stars not long before its capture, while most are dominated by older populations that have been burning quietly for billions of years before their final fall. Beyond starlight, the streams sometimes carry gas that can be traced in the radio, though the gas is often stripped earlier by the hot circumgalactic medium and falls on a different path, lighting brief flows or cloudlets that may later rain on the outer disk. The balance between what remains bound and what escapes depends on the speed at which stars are flung during the disruption, and on the local escape speed set by the halo, and in Andromeda many disrupted stars remain within the system, lengthening the outskirts and thickening the faint halo. Taken together, the cold streams and shells transform the outer halo from a smooth gradient into a legible archive. They show that the Andromeda galaxy has been eating small companions in recent cosmic time, that the diet has ranged from light and metal-poor dwarfs to richer systems that once hosted clusters, that infall has been anisotropic along preferred directions, and that the halo potential is mostly smooth, yet not perfectly round. They fix scales where mass must lie, they fix epochs for past passages, and they forecast what will happen as new companions arrive, because the same physics will draw new ribbons and stack new shells. As the narrative steps inward, these fragile structures remain a guide, for they are both the handwriting of gravity at the edge and the source of stars that later settle into the thicker parts of the disk and bulge, and they remind the observer that calm, faint features can carry the loudest truths about growth, balance, and the quiet persistence of time. The companions of the Andromeda galaxy gather like small towns around a luminous city, some close and bright, some faint and far, all moving under the same deep pull, while carrying their own histories written in star counts, gas content, and the slow churn of chemical enrichment. The most prominent companions sit near the bright disk and show contrasting personalities. One is a compact elliptical body with a steep rise in light toward a tiny centre, a system that seems to have lost much of its outer structure and now holds a dense core of old stars with only sparse traces of gas. Another is a more diffuse elliptical neighbour with a soft glow slightly flattened, showing a modest range of stellar ages and a few lingering pockets of dust that hint at past gas and at quiet star formation that likely ceased long ago. Their positions near the main galaxy and the distortions seen in their outer isophotes suggest that tides have shaped them, pulling at their stars and lifting streams that are now traced by deep imaging. Farther out, dozens of dwarf spheroidal systems drift in the halo. These are low-surface brightness collections of ancient and intermediate age stars, often lacking gas, with star formation histories that usually end early. Their sizes are small, their internal motions are low, yet those motions still exceed what starlight alone would bind, implying that each carries a heavy share of dark matter. A minority of companions still hold gas and form stars. These tend to live at larger radii where the hot halo of Andromeda is less dense, and where the headwind they feel as they orbit is weaker. The pattern fits a simple picture in which the circumgalactic medium strips gas from small galaxies that plunge deeper, a process that quenches star formation and turns blue dwarfs into red dwarfs over time. The chemical fingerprints of these satellites vary with their mass. Heavier dwarfs reach higher abundances of heavy elements because their deeper wells retain the products of stellar winds and supernovae, while lighter dwarfs lose much of this material to space and remain metal poor. When astronomers measure the distribution of metallicity within a single dwarf, they often find gradients with more enriched stars near the center and poorer stars in the outskirts, a sign that gas cooled and settled toward the middle during the final episodes of star formation. The orbits of these companions are mostly inferred rather than directly drawn, because sideways motions are faint at such distances, but line-of-sight velocities already sketch a pattern in which groups of satellites share common directions around Andromeda. Several companions appear to lie in a rough plane that is tilted relative to the disk, and within this plane their velocities hint at coherent rotation, though the degree of coherence remains debated as new. Measurements add or subtract members from the set. If such a plane is real and long-lived, it may record the infall of a bound group that entered along a filament and has not fully dispersed, or it may be a chance alignment in a snapshot of an ongoing reign of dwarfs. The simple fact that many small systems fall in along preferred directions reflects the larger web from which they come, where filaments funnel material into the main halos. Some of the satellites cluster by type. A pair of dwarf ellipticals of similar brightness sits to one side of the halo close to one another on the sky, and likely sharing a related history before they were captured. A swath of ultra-faint dwarfs crowds another sector, where deep surveys have pushed the detection limit low enough to find systems with only a few thousand stars. The census of these faintest companions is still incomplete, and every new discovery shifts the statistics on how satellites distribute in number and brightness. The classical puzzle of missing satellites, where early simulations predicted many more low-mass sub-halos than the number of dwarfs observed, has softened as deeper searches uncover fainter members and as models show that only a fraction of subhalos ever light up with stars. Still, the uneven spread of discovered companions around Andromeda raises questions. Some gaps may be real marking directions where accretion has been sparse, while others may be observational, tied to the difficulties of finding very low contrast objects against a field of foreground stars. Tidal interactions between Andromeda and its companions shape both partners. The compact elliptical shows a bright core and a truncated envelope that many studies interpret as the remnant of a larger disk galaxy, whose outer stars and gas were stripped during past passages, perhaps contributing to ring-like features seen in the inner regions of Andromeda. The more diffuse elliptical neighbour exhibits boxy outer contours and low-level dust that signal a stirred structure and a recent episode of mild activity now fading. Dwarf spheroidals near the main disk carry tidal tails that align with known cold streams, and in a few cases the remaining core of a dwarf can be linked kinematically and chemically to a particular ribbon in the halo, confirming the picture of ongoing accretion. Globular clusters orbiting Andromeda may have arrived with companions. Several clusters share the motions and metallicities of nearby streams, and compact star clusters are also found in some dwarfs that are still intact, especially in heavier satellites that manage to form multiple generations of stars. These clusters act as mileposts that help trace orbits and strengthen the ties between present companions and past debris. Gas-rich satellites at large distances present another kind of story. They show clumpy star formation in small knots, with young blue stars scattered across modest disks, and their rotation curves rise gently, before flattening a scaled-down echo of the main galaxy. The balance of pressure from the hot halo and the internal gravity of each dwarf decides whether gas remains bound and whether new stars can form. When a gas-rich dwarf swings in on a path that dips into denser regions of the circumgalactic medium, its gas can be pushed backward, forming tails that shine faintly in the radio, and sometimes leading to short-lived bursts of star formation as gas is compressed. The variety of companions offers a way to test galaxy formation physics on small scales. If dark matter were warm enough to erase the smallest substructure, the number of ultra-faint dwarfs would drop, and the thinnest streams would be smoother than observed. If dark matter formed many compact massive clumps, streams would show stronger kinks than are commonly seen. The actual pattern in Andromeda seems to prefer a middle path, in which many low-mass subhalos exist, but only some gather gas and ignite stars, and in which the halo is mostly smooth with gentle lumps. The satellites also help weigh the main halo, by treating each companion as a tracer in a central potential, and by accounting for the mix of bound and in falling orbits. The spread in velocities points to a total mass, in line with that inferred from rotation curves, hot gas, and the timing with the Milky Way. In this sense, each dwarf is a moving test weight, a quiet participant in the broader balance. The companions live in time as well as in space. Their star formation histories show pauses and renewals that line up with likely pericenter passages, and their chemical tracks preserve episodes when inflowing gas refreshed their reservoirs, or when feedback drove winds that carried metals away. Taken together, the ensemble around Andromeda forms a living record of assembly. It shows that the galaxy grows by gentle eating rather than by violent feasts in recent epochs. That environment quenches the small thirst that direction matters, because the cosmic web delivers material along set lines, and that even the lightest companions leave marks far beyond their size. As the path of the narrative bends inward from the outskirts, into the warped border of the disk, these satellites continue to whisper guidance. They set the angles at which tides tug, they set the places where streams cross. They seed the clouds that may later feed the spiral arms, and they trace a choreography in which a great city and its towns move together through a dark landscape that shapes them all. The approach of the Andromeda galaxy toward the Milky Way is measured with a patience that matches the slow rhythm of galaxies turning tiny shifts on the sky, and small changes in spectral lines into a three-dimensional motion that speaks across deep time, and in this careful work the difference between a static universe and a living one becomes tangible. Along the line of sight, the light from Andromeda is gently pulled toward shorter wavelengths, a sign that the galaxy is moving nearer, and this shift is read by spreading the light into a spectrum and matching the patterns of known atomic lines to the positions recorded by the instrument. The size of the shift is small compared with the great recessions seen in distant galaxies, yet it is firm, and when translated into speed it yields a value that lies in the range of a few hundred kilometers per second, a pace that would cross the distance from Earth to the Moon in a matter of days, but that requires billions of years to span the gulf between two great stellar cities. This line of sight component, while essential, is only one side of the motion. To know whether the meeting will be head-on, or a glide that brushes past astronomers, must measure the sideways drift on the sky, a proper motion so small that it takes many years and the sharpest imaging to see it all. Space-based observatories lock their fields to quasars that sit at cosmological distances and act as fixed pins on the fabric of the sky, and against these pins the bright knots and compact star clusters in Andromeda are compared across epochs. When the field is aligned to the same frame each time, the tiny average shift of Andromeda's stars can be seen, and from that shift a tangential speed is derived. The measured sideways motion is modest compared with the approach speed, but it is not zero, and that modest value matters because it decides whether the future path will spiral into a direct encounter or arc into a long dance with multiple passes. To place this motion into a proper frame requires removing the effect of Earth circling the sun of the Sun, orbiting the centre of the Milky Way, and of the Milky Way itself drifting within the local group. Each of these motions can mimic or mask the true movement of Andromeda if left uncorrected. The orbit of Earth is known to exquisite precision from radar reflections and spacecraft tracking. The path of the Sun around the Milky Way is inferred from the motions of nearby stars and from the structure of the spiral arms and bar, while the overall drift of the Milky Way within the local group is estimated by combining the motions of many galaxies. When these contributions are subtracted, the cleaned vector of Andromeda's movement remains. The final picture shows a galaxy that is indeed on course to meet the Milky Way, with a small sideways component that is large enough to prevent a perfect bullseye, but not large enough to avoid interaction. On the timescale of a few billion years, the separation will narrow, the halos will begin to overlap strongly, and the first close passage will stir both disks. The timing of this future depends subtly on the total mass enclosed within the two halos and on how much mass lies in the shared envelope of the local group. A heavier combined mass deepens the gravitational pull, shortens the time to the first passage, and can draw the paths into a tighter curve. A lighter mass does the opposite, allowing a broader arc and a longer wait. The sideways motion also sets whether the first encounter will pass above or below the midplane of the Milky Way, and which spiral arms will feel the strongest tides. In a direct head-on scenario, the central regions would cross more closely, and bars and rings might be driven quickly, while in a glancing pass the outer disks would feel the first pull, and the internal response would ripple inward more gradually. Observations of other galaxy pairs caught at different stages offer analogues that guide these expectations. Some show broad tidal tails that flow away like giant ribbons. Others show ring-like waves expanding through the disk, where a nearly centered passage has sent a density pulse through the stars and gas. The approach of Andromeda is not merely a prediction of distant astronomy. It is a test bed for the entire chain of measurement. The line of sight speed must be tied to stable references. The sideways motion must be measured against nearly motionless beacons, and both must be placed into a common frame without hidden offsets. Independent methods aim at the same goal. Water masses in compact star-forming regions can be tracked with radio observatories that combine signals from antennas spread across continents, creating an instrument with the sharpness of a telescope the size of Earth. And these masers can provide both proper motions and distances. Star clusters within Andromeda, because of their compact shape and brightness, serve as repeatable targets across years, while background quasars define the unmoving grid. The agreement among these approaches increases confidence that the true vector is known within reasonable uncertainties. With a motion in hand, models can be run forward. Test particles representing stars' gas and dark matter are set within potentials that match the inferred masses and shapes of the two galaxies. The particles are allowed to evolve under gravity, and the codes draw possible futures in which spirals wind and unwind, bars strengthen and weaken, and halos exchange energy until a merged remnant forms. In many runs, the first passage happens in about 4 billion to 5 billion years from now, with a second and third passage following, as friction within the halos robs the orbits of energy, and the two centres settle into one. The final shape often resembles a large elliptical galaxy, with a deep envelope of stars and a central structure that preserves some memory of the progenitors. Gas physics adds complexity. During close passages, gas clouds can be compressed, triggering bursts of star formation that light tidal arms and bridges. In other places, gas may be shocked and heated, delaying starbirth until it cools. The hot circumgalactic media of the two galaxies will mix, and some gas may be driven outward, while some sinks inward to feed central growth. All of these processes depend on the exact path set by the measured vector, and so the precision of the proper motion feeds directly into the quality of the forecast. The approach also matters for the wider local group. Satellites now orbiting Andromeda and the Milky Way will feel a changing landscape of forces as the halos draw together. Some companions may be captured by the other giant, some may be flung onto new orbits, and some may merge with their hosts sooner, because tidal fields grow stronger. Streams in the outer halos will be stretched and bent, and their shapes will record not only past interactions with small dwarfs, but also the beginning of the large encounter. The intergalactic medium between the galaxies may brighten in faint emission, as shocks and compression increase during the approach, although much of this will remain difficult to detect. The Sun's own path around the Milky Way will carry it through different parts of the disk during these epochs, and at the time of first passage the local sky will show Andromeda grown large, its spiral pattern stretched and torn by tides, yet the local gravitational influence on the solar system will remain governed overwhelmingly by the Milky Way until the merger nears completion. Through all of this, the method is a lesson as much as the result. The measurement of a sideways drift that is smaller than the width of a human hair seen from thousands of kilometers away becomes the hinge on which the fate of two giant galaxies turns. The combination of line-of-sight speed, proper motion, and carefully corrected reference frames allows a narrative of the future to be drawn with confidence that is modest but meaningful. The Andromeda Galaxy is not standing still. It is sliding across the sky at a pace that a patient eye can record, and it is closing the gap with a steady approach that neither rushes nor hesitates. The meeting is written not as a sudden event but as a chapter of long duration, whose opening lines have already been read in the shift of a spectral line, and in the tiny steps of a bright cluster against the pinned pattern of distant quasars. In that knowledge, the quiet present takes on a different flavour, for the calm disk and the faint halo exist already within the pull of a future that will reshape them both. The outer disk of the Andromeda Galaxy looks calm from a distance, a luminous plate with faint arms and a clean rim, yet a closer view shows that the border bends and tilts in a slow undulation, as if the starlight and gas ride a gentle tide that never quite settles, and the warp that results becomes a ledger of past nudges and the present pull of companions and halo. Atomic hydrogen, cold and patient, sketches the shape most clearly because gas responds to tides and pressure more quickly than stars, and its map shows that one side of the disk rises above the midplane, while the opposite side dips, with the angle changing gradually with radius, so that the disk not only tilts, but also twists, an effect that carries a memory of the torque applied by a passing dwarf or by the continuous draw of a nearby companion that has not yet fully merged. Starlight at the edges faint but not mute, and when counts of red giant branch stars are traced far outward, they echo the gas by leaning slightly in the same direction, a sign that the warp is not a skin of gas alone but a bend in the broader structure, where gravity and pressure find a shared compromise, and this shared compromise continues to evolve as streams cross the outskirts and as the hot circumgalactic medium presses lightly on the rim. The warp does not stand as a single simple curve, it precesses slowly, meaning that the line of nodes where the tilted outer disk crosses the inner plane rotates over time, and this rotation can be read in the way the position angle of the outer isophotes drifts with radius, and in the way the kinematic major axis of the gas differs from the photometric axis, and from these gentle mismatches the mind infers a long conversation between disk halo and passing companions in which none speaks loudly yet all speak for a very long time. Where the warp lifts the gas, the surface density falls and the star formation rate wanes, because cold clouds are stretched thin, and the ultraviolet light of background sources can slip more easily between them, while where the warp dips the surface density gathers, and in these lower pockets the gas can cool and condense more readily, so that faint beads of young stars may appear even at great distances from the centre. And this asymmetry in star birth becomes a tracer of vertical shape as much as of radial supply, a subtle weather map painted in blue knots along a bent shore. The warp also accompanies a flare, a slow thickening of the outer gas layer, and of the stellar scale height with radius, because the vertical restoring force of the disk weakens where the surface density drops, and where the halo's pull competes at a shallower angle, and the result is an edge that looks softer and more layered in profile than the inner parts, with older stars floating slightly above younger ones, and with the oldest populations showing the broadest distribution, a fingerprint of gradual heating by tides and by the passage of giant molecular clouds long ago. Rings and arcs within the disk, some nearly closed and others broken like crescents, intersect the warp and sometimes follow it, and these structures are not merely decorations but records of radial waves set off by past encounters, waves that carry gas and stars inward and outward, and that pile material where their crests linger, and where a crest meets the low side of the warp, the density rises a little higher, and star formation may light the curve more brightly than on the lifted side, yielding a lopsided pattern that would look like a flaw in a quick glance, but that resolves under patient study into evidence of a dynamical rhythm. Kinematic maps add another layer of meaning, for they show that the line of maximum rotation bends with radius, and that the outer gas sometimes leads or lags the inner expectation depending on azimuth, and these shifts tell of streaming motions along arms of shocks where gas slips through a spiral pattern that itself may be slightly tilted with respect to the inner disk, and of the quiet action of asymmetric drift in the sparse stellar population, where random motions count as much as rotation in holding orbits together. Taken together, they deliver a picture in which the warp is not a separate object, but a mode in the living disk, a mode excited by tides and maintained by the continued inflow of material along the halo's filaments. The likely drivers stand close at hand, for the compact elliptical companion that orbits near the bright centre shows scars of stripping that imply close passages, and the diffuse elliptical neighbour carries distortions that point to a stirred past, and both have had time to tug on the outer gas and stars. A single, nearly polar sweep by the compact companion could tilt the edge and produce the observed twist, while a slower inclined tidal pull from the diffuse neighbour could keep the warp from damping away, and the many dwarfs that move in loose planes around Andromeda add their small but cumulative torques, so that the warp is the vector sum of many hands, some recent, some older, none alone decisive but altogether persuasive. Models that follow orbits within a flattened dark halo replicate the broad sense of the warp only if the outer halo is not perfectly spherical, because a slightly oblate or triaxial mass distribution exerts a torque on a misaligned disk that drives precession and sets the pattern speed of the twist, and the observed rate implies a halo that is close to round but not exactly round, a conclusion that fits the behaviour of the stellar streams and the shapes of globular cluster orbits, and that in turn influences how gas flows inward over time, and how long the warp can live before it either fades or is reset by the next encounter. Vertical waves ride on top of the tilt visible as corrugations where star counts rise and fall above and below the midplane, likely set by bending modes that were excited when a satellite skated under the outer disk, and these waves travel slowly inward and outward, changing phase with radius, so that a crest in one ring can be a trough in the next, and in the cool gas the same pattern can appear as paired lanes, where dust piles slightly higher on one side and slightly lower on the other, a pattern that can be measured by the reddening of background stars and by the slight shift of atomic hydrogen emission in velocity space. The warp has consequences for the future dance with the Milky Way, because the angle at which the outer disk is already tilted will influence which sectors feel the earliest tidal pull when the halos begin to overlap more strongly, and parts of the rim that already lift may be drawn farther upward into tidal bridges, while the dipped side may yield first to a spiral of stripped gas. And because rings and corrugations seed preferred lines of weakness, they will guide where star formation lights up in the first close pass shaping arcs that will later fade into the envelope of the merged remnant. Yet the warp does not speak of disruption alone. It also signals resilience, for the inner disk remains well ordered, and the warp carries only a small fraction of the mass, so that the city of stars holds its shape even as the countryside bends in the wind, and the slow procession shows that the system has had time to absorb past impacts and to settle into a balanced motion rather than a chaotic tumble. In the quiet present, the warp offers a way to weigh invisible things, to read the shape of the dark halo and the memory of recent visitors without seeing either directly. And it also offers a way to time events, because the degree of twist and the spacing of vertical waves act as clocks that tick in millions of years rather than in minutes, clocks that say how long ago a dwarf passed close, how quickly the line of nodes turns, and how far the disk has drifted since the last strong nudge. And in this sense, the bent rim is less a flaw than a calendar written in starlight and gas. As the narrative moves inward, the warp remains in the mind as a soft boundary condition, a reminder that the bright arms and dust lanes do not float in a perfect plane, but travel through a field that is slightly askew, and that every map of the inner structure must be read with that gentle tilt in place, because the outer disk sets the frame in which the inner spirals wind, and in which the bulge holds steady against tides that come from beyond. The spiral arms of the Andromeda galaxy appear as soft bands of light wrapped around a pale disk, yet they are not static decorations but slow density waves that move through the disk and gather material as they pass, and within these moving ridges cold clouds or compressed stars ignite, and blue starlight briefly marks the crests before time carries each cohort onward. A spiral arm does not carry the same atoms forever. Gas and stars drift into the ridge linger as orbits are gently turned by the higher density, then drift out again on the far side, so that the arm is a place of passage where the physics of compression, cooling gravity and feedback briefly align to build clusters and to trace the galaxy in bright threads, visible across great distance. Molecular clouds supply the raw mass for this cycle. They are cold regions where atoms bind into molecules where temperatures rest only a few tens of degrees above absolute zero, and where the balance between internal pressure, magnetic support, and gravity can be tipped by a small push. Entry into the spiral wave provides that push. Streams of gas converge, shocks form the outer layers, shield the interior from starlight cooling accelerates, and the cloud fragments into dense cores that spin slowly and collapse into stars. The most massive newborns blaze in blue and white, pour out ultraviolet radiation that ionizes the surrounding hydrogen, and blow winds that hollow the parent cloud into bright-edged cavities. These glowing shells of ionized gas outline the front edge of the ridge like beads on a faint necklace, and just downstream young clusters gather, while farther along the lane, older clusters begin to fade toward white and yellow as their brightest members die and their light shifts with age. This ordered sequence from dark dust lane to glowing gas to blue clusters to aging groups records the flow of material relative to the arm and turns the disk into a readable conveyor of time. Kinematic maps confirm the presence of gentle shocks and streaming motions. Gas slows slightly as it enters the ridge and accelerates as it leaves, while stars less easily compressed feel the wave as a subtle tug that changes orbital phase rather than as a true stop. Young clusters move with small scatter around the mean rotation because they have not yet been stirred by many encounters with other clouds and waves. Older stars show a broader spread in speeds and heights above the plane, and this difference in scatter builds the visible rule that the thin disk is young, while the thicker layers hold populations that have been heated by many passages through spiral arms and by the memory of past tides. Star formation is paced by feedback. Radiation and winds from massive stars carve bubbles. Supernova explosions follow within only a few million years and connect the bubbles into larger cavities. Gas along the rims is compressed again, and new stars spring up in bright arcs that face inward toward cleared centers. If feedback runs too strong, a region pauses. If it is modest, the same feedback stirs gas without dispersing it, priming the next round of collapse. Thus the arms act as self-regulating engines, whose output depends on how gas flows in from larger radii, and on how the previous generation has shaped the local medium. Some sectors of Andromeda show stronger grand design arms, where two main ridges sweep across much of the disk with high contrast. Other sectors are more fragmented with short arm pieces that break and reconnect a pattern that likely remembers a tidal nudge that favoured compression along one flank and stretched the pattern along the other. Intersecting the arms are ring-like features nearly closed waves that may have been set off by a past passage of a compact companion through the inner disk. Where such a ring meets a spiral crest, gas piles higher and star formation brightens so that knots of blue light cluster along the intersections like storms gathering where two fronts cross. Thresholds set where arms can light. Gas must reach a surface density above a certain level to cool and fragment rapidly, and the outer disk often lies below that level, except where the warp or a stream has raised the local supply. Closer to the center, gravity tightens and shear grows so clouds can be torn before they collapse, unless they are massive and well shielded. The rate and scale of cluster birth therefore depend on a balance among self-gravity rotation and pressure from the wider environment. Dust traces this balance. It both hides and reveals. It hides the hearts of clouds from ordinary starlight, allowing molecules to survive and cause to cool, and it reveals the streams of cold gas by reddening and dimming background light along curved lanes that outline the arms with dark ink. In the outer disk, thin veils make the halo and arm stars blush. In the inner regions, dense walls carve sharp silhouettes. Infrared observations translate these veils into maps of temperature and column density, while radio maps of atomic hydrogen and molecules mark the reservoirs that feed the current generation and hint at where the next ridge crossing will seed collapse. Clusters provide clocks. The hottest blue stars live only a few million years, so their presence alongside bright ionized gas marks very young age. When those stars die, a cluster quickly shifts to a whiter light and loses its surrounding glow, moving it a step along the conveyor of the arm. By placing clusters across the arms and reading their ages, astronomers retrieve a timeline wrapped around the disk that confirms the direction of flow and the speed of the wave relative to rotation. Not every bright patch is simple. Some luminous knots resolve into complexes where many clusters form across tens of millions of years as gas streams through a long-lived pocket. Inside such a complex age grades with distance from the dust lane and newborn stars remain hidden in thick cocoons that shine only at long wavelengths until feedback opens seams through which light escapes. Spiral arms also shape the journey of heavy elements. Stars forge heavier atoms and spread them through winds and explosions. The next generation draws from gas that is little richer, and over time inner regions tend to show higher abundances than outskirts, because cycles are faster and mixing is stronger where densities are higher. In Andromeda, abundance gradients run outward from the centre with gentle plateaus where rings or strong arms have stirred and shared material across wide arcs. These gradients are not mere decoration. They set how efficiently clouds cool and therefore modulate the next round of star formation. All of this unfolds under the calm rule of gravity and rotation. The pattern persists because the disk still receives gas from the halo, and because the combined mass of stars, gas and dark matter sets a rotation curve that allows the wave to live. If supply dwindled, the arms would fade toward a fossil pattern. If the curve changed strongly, the wave would shear away. Instead, Andromeda shows a balanced state in which subtle asymmetries, rings and warps nudge, but do not erase the grand design. As the narrative turns inward toward dust lanes closer to the bulge and toward the crowded heart, the spiral arms remain the living borders between quiet outskirts and busy inner structure. They carry the memory of past encounters in their asymmetries. They host the present generation that sketches the galaxy to any casual glance. They gather and release gas in a rhythm that will shape how the central regions feed and how the disk will respond when tides from the Milky Way rise in ages to come. They are not ornaments but engines, and they sustain the calm whirl with a quiet cycle of gathering ignition, clearing and renewal that proceeds without haste and without rest. Dust lanes thread the disk of the Andromeda galaxy like soft rivers of shadow, guiding the eye along curves that wrap toward the centre and splitting the pale starlight into bright and dim bands, and behind these graceful strokes lies the cold architecture of molecular clouds that hold the next generations of stars in dark, slow preparation. Dust is not a uniform fog, but a mixture of tiny grains made of carbon-rich compounds, silicates, and ices that grow coats as they drift through colder regions. These grains scatter and absorb blue light more strongly than red, so a lane drawn across the disk dims and reddens, the stars behind it, and this selective veil allows maps of dust to be drawn by comparing the colours of many background stars to the colours those stars would have if no veil lay before them. In the brightest inner arms, the lanes run close to the leading edges of the spiral pattern, where gas streams in and compresses, and along those edges the dust gathers into ridges that mark the places where pressure rises, and where cooling outpaces heating, so the atoms bind into molecules and clouds condense. The coldest parts become opaque to ordinary starlight, yet they glow faintly in the infrared, where warmed grains radiate the energy they have absorbed. This glow is a second way to read the lanes. At medium infrared wavelengths, the warmth of small grains and complex carbon molecules paints the outlines of clouds in soft light. At longer infrared wavelengths, larger cooler grains trace the heavy reservoirs that will feed stars if gravity wins the quiet contest against internal motions and magnetic support. The molecules themselves are difficult to see directly, because the most abundant one, molecular hydrogen, does not radiate easily at the low temperatures of the clouds. Astronomers therefore follow other molecules that do shine with carbon monoxide, the most common proxy, and surveys that map carbon monoxide across Andromeda's disk reveal long arcs of emission that coincide with the darkest dust lanes. Where carbon monoxide brightens, the surface density of molecular gas rises, and where it fades, the clouds thin into atomic hydrogen that spills farther out into the warped outskirts. The balance between atomic and molecular gas depends on pressure, metallicity, and the local radiation field. In regions closer to the center where the radiation field is stronger and the heavy element content is higher, dust grains are more abundant and better at shielding the interior of clouds so the molecular fraction increases. Farther out where heavy elements are scarcer and the field is weaker, the transition occurs at higher column density, and the lanes are more delicate. Within the lanes the gas does not sit still. It streams along with the disk guided by the gravitational pattern of spiral arms slowed slightly, where the crest of the density wave stands and accelerated again downstream. Shear from differential rotation stretches the clouds, while shocks at arm entry compress them. Magnetic fields thread the gas and can align elongated filaments along the arm, lending the lanes a texture of parallel strands that is visible when dust polarization is measured. In regions where the spiral pattern meets a ring-like wave driven by an earlier encounter, the geometry of forces changes, and there the dust darkens into knots and forks where flows converge. Young stars born inside the densest cores emerge in a sequence set by feedback and drift. At first they remain hidden behind thick columns of dust, their presence betrayed only by warm infrared light, and by faint maser lines, where water or other molecules act as microscopic lasers. Soon the strongest radiation from massive newborns strips the cloud skin into a glowing shell of ionized hydrogen, a round or blistered wall that wraps the cluster and faces the dust lane as if answering a call. Farther from the lane where time has passed, clusters expand, winds combine and supernova shocks connect cavities into larger bubbles that push on neighboring clouds. In this way, the lanes regulate star formation, serving both as cradles and as boundaries. If gas inflow from the halo and outer disk replenishes the lanes at a steady rate, the cycle persists without hurry. If supply falters, dust thins, molecular gas declines, and the bright chain of star birth loses contrast. The locations of the darkest lanes are not perfectly symmetric across the disk. On one side of Andromeda, the main inner lane runs closer to the bulge and is sharper, while on the opposite side lanes split and reconnect, a sign that tides, and the slight tilt of the outer disk shift the pattern speed and the strength of compression from sector to sector. In some radial bands, dust forms nearly closed rings with only narrow gaps, and those rings may represent the fossil wake of a companion that passed near the centre and sent a density wave outward. Where a ring crosses a spiral arm, the lane deepens, carbon monoxide brightens, and clusters pile up, creating luminous beads that later disperse but leave behind an imprint in the chemical record. That record appears as gradients in heavy elements measured across the disk. Dust is both product and agent of those gradients. It carries atoms forged in earlier generations of stars, and it helps shield and cool the gas that will form the next generation. Over many cycles, inner regions accumulate higher abundances, and the lanes grow more efficient at fostering molecules there. Yet radial flows driven by bars, rings, and warps leak heavy elements outward, flattening the gradients into gentle slopes with small plateaus where mixing has been strongest. In Andromeda, these plateaus line up with the ring-like structures, and with strong arms as if the lanes are stirred over wide arcs by the same broad rhythm that set their paths. The vertical structure of dust adds a quiet complexity. In the inner disk, lanes are thin and pressed close to the midplane, while in the outer, flared regions they broaden and lift, so that faint veils redden halo stars above and below the plane. Corrugations, small waves that ripple the disk vertically modulate the height of the lanes, so that in one ring the dust rides slightly above the average plane, and in the next it dips below. These corrugations likely carry the memory of a satellite that skimmed the edge, tickling the outer layers into a long-lived bend. The central bulge influences the lanes as well. As orbits crowd near the bulge, the pattern of allowed paths changes and dust follows families of orbits that can be skewed relative to the outer spiral geometry. This skew is visible as twisting lanes that wrap more tightly and appear to enter the bulge at angles that differ from those of the arms in the outer disk. In these regions, gas can shock along standing lines and be funneled inward, feeding the central star cluster, and perhaps the region around the central mass on very long timescales. The dust lanes therefore act as conveyor belts that deliver material from the spiral arms to the inner few hundred parsecs where the orbital families are more complex and where the next section of the narrative will linger. The lanes also serve as a fragile window into time because their contrast depends on the balance between formation and destruction of grains. Supernova shocks can shatter grains while the calm growth of mantles in cold regions rebuilds them. Radiation from stars strips ices in warmer zones, while in denser cold pockets, ices grow and change the spectral signature of the infrared glow. By reading these signatures across the disk, observers trace the recent weather of star formation and feedback. In every sector, dust is both an obstacle and a guide, hiding what it shields, while revealing the flows and pressures that sculpt it. It marks where the gas has slowed, where gravity gathers strength, where star formation has recently begun, and where young stars have just cleared the veil. In the Andromeda galaxy, dust lanes and molecular clouds are not mere accents on a luminous canvas. They are the cool, patient framework that sets the pace of change and holds the instructions for how the next stars will be made, how the arms will keep their contrast, how rings will glow and fade, and how material will drift inward toward the crowded heart. The lanes define the texture of the disk and anchor the present to both past and future, and their dark light writes the most legible story of the living, moving, self-regulated galaxy that turns in quiet persistence beyond the luminous center. The ancient populations in the halo of the Andromeda galaxy surround the bright disk like a faint time-worn mantle, and within this mantle the oldest stars and the great globular clusters carry a record of early assembly, written in age, chemistry and motion, that persists even after long mixing. Far from the spiral arms, the starlight thins into a soft field, dominated by metal-poor giants, blue horizontal branch stars and reliable variable stars whose steady rhythms act as clocks that always strike the hour of great antiquity. These traces reveal that much of the halo formed in the first few billion years after the earliest stars lit with many components older than 10 billion years, and that later accretion continued to add layers without erasing the signature of the first epoch. The distribution of heavy elements among halo stars, when plotted as a simple count versus enrichment, shows two broad peaks that hint at an inner component that is somewhat richer and a more remote component that is poorer. A pattern that echoes the tale told by the faint streams and shells of Section 5, and that suggests a history where a central well formed early, and then many small systems were folded in along filaments. Along many lines of sight, the outer halo turns bluer and more metal, poor with radius, while toward the inner regions a mild gradient rises, then flattens, where ring-like waves and minor mergers have stirred the mix. Kinematics add a shape to this chemistry. In the inner tens of thousands of light-years, halo stars show a preference for elongated paths that lean toward prograde motion with the disk, as if some fraction were heated disk stars that were lifted long ago by tides. Farther out motions become more radial, and the preference for prograde or retrograde weakens, consistent with a halo grown from many small infalls whose orbits were only loosely aligned with the main spin. In a few sectors, coherent flows remain, betraying the recent arrival of a dwarf that has not yet fully dissolved. There, halo stars and globular clusters share the same speeds and serve as bright seams stitched through the otherwise smooth cloth. Globular clusters are the most legible letters in that cloth. Andromeda holds a richer system of clusters than the Milky Way, with hundreds that range from dense, compact classical clusters to unusually extended bodies whose faint outskirts blur into the field. Many clusters are as old as the oldest halo stars their ages, told by the turn-off points in their color magnitude diagrams, and by the heavy element ratios in their red giants, which carry the imprint of rapid early star formation when massive stars ruled chemical evolution. Others are somewhat younger with ages of several billion years, and these likely arrived with captured dwarfs or formed during minor interactions that compressed gas in the outskirts. The chemistry of clusters marks their origins. Clusters associated with metal-poor streams show low heavy element content, and enhanced signatures of rapid enrichment clustering in the same space where dwarf debris flows. Clusters that sit closer to the center often show higher metallicity and orbits that suggest they once belonged to a thicker, more turbulent early disk or bulge that was stirred. A few clusters move on retrograde orbits that cut against the main spin. These odd paths are a quiet proof of past accretion because capture does not respect local rotation. The extended clusters in the far halo are a puzzle of their own. Their stars are old and metal-poor, but their sizes are large and their surface brightness is low, as if they straddle the boundary between normal clusters and the smallest galaxies. Some may be the surviving nuclei of dwarfs that lost their envelopes. Others may be clusters that puffed up in a calm tidal field after being placed on wide orbits. Their existence argues that the outer halo has been a gentle place for long stretches, because tides that were too strong would have shredded them. The field halo beyond the luminous disk shows breaks in its radial profile, with the density of stars falling more sharply beyond a certain radius. That break likely records a transition from an inner component built through early, relatively well-mixed events to an outer component composed of more recent, less mixed infall. The stars that populate the very far outskirts sometimes bunch along narrow planes that also carry faint streams, implying that parts of the halo formed from the slow unspooling of bound groups, rather than from the quick feeding of solitary dwarfs. Variable stars add precision to this wide picture. The recurrent beat of ancient pulsators marks distances and confirms that many halo features are as far out as maps suggest, and the uniform ages of these variables tighten the case for an early start to the halo. Blue straggler stars, which look younger than their surroundings, sprinkle the field and certain clusters. Their likely formation through mergers or mass transfer inside old binaries shows that even ancient populations carry a quiet internal life that can mimic youth without requiring new gas. The motions of halo stars, when decomposed into radial and sideways components, reveal that the outermost parts prefer plunging orbits, while the inner parts carry more sideways balance, and this division explains why streams linger longer at great distances, and why the inner halo smooths faster into a nearly featureless glow. Chemistry and kinematics, when combined star by star, allow substructures that are otherwise invisible to stand out. A tight clump in velocity space, with a shared heavy element pattern, becomes the fossil of a long-dissolved dwarf, and multiple such clumps draw a family portrait of accretion that connects to the cold stream still visible as distinct arcs. Close to the disk, a diffuse population of stars with intermediate metallicity and thicker orbits weaves between the thin disk and the classical halo. These stars may be heated disk members or the remains of an early massive merger that puffed the young system and then settled. Their presence matters because they carry angular momentum and can torque the disk over long times, linking ancient events to present geometry. The halo also holds interstellar relics too faint to trace directly, for the hot circumgalactic medium permeates the same space and is enriched by the deaths of old stars as shown by absorption seen against faraway beacons. Heavy elements do not only live in stars, they wander in the thin gas of the halo as testament to winds, fountains, and gentle outflows that have slowly marinated the outskirts. This metal-bearing gas can fall back in cold clumps and feed star formation, where warp and ring concentrate the flow, connecting the most ancient envelope to the present cycle in the disk. Puzzles remain that keep the ancient halo alive as a field of inquiry. Some clusters show internal spreads in certain light elements that point to multiple early episodes of starbirth, inside a common well-raising questions about how small systems hold gas long enough to recycle it. A few remote clusters sit where no obvious stream runs, hinting that their parent systems were fully mixed away, or that these clusters migrated through subtle resonances over long times. The balance between a smooth dark halo and lumpy dark substructure remains under test because a granular field would thicken streams and heat-extended clusters over billions of years, and the present coherence of many features argues that the grain is gentle. Even the simple count of extremely metal-poor stars in the outermost fields challenges models, because the fraction of the very oldest, most primitive survivors sets how quickly the first rounds of star formation proceeded, and how thoroughly later events mix the debris. Through all these threads, the message is calm and persistent. The ancient halo is not a static fringe, but a living archive whose pages turn slowly. Ages tell when the first chapters were written. Chemistry tells where the ink was made. Motion tells how each page was bound to the next. Globular clusters serve as illuminated capitals that stand out across the parchment. Streams act as marginal notes that can still be read. Together they say that the Andromeda galaxy grew by early rapid assembly, joined to a long season of quieter accretion, and that the oldest light still shapes the frame within which the younger disk draws its spiral, the bulge holds its weight, and the centre turns with a patience that measures time in billions of years. The central light of the Andromeda galaxy swells into a broad rounded rise that looks at first like a single classical bulge, yet closer study shows layers, asymmetries and streaming motions that suggest a more complex heart where an older spheroid, a possible bar that is seen at an angle, and embedded rings or lenses overlap and share the same small space. Photometric profiles taken along the major axis and minor axis do not match the clean curves expected for a simple spheroidal component. Instead, the brightness falls more slowly along one direction. The esophotes look slightly boxy rather than perfectly oval, and faint twists in position angle appear as radius changes, hints that some of the central light is supplied by stars trapped in elongated orbits that a bar would support. Kinematic maps give a second voice to this picture. Within a few thousand light years of the center star show rotation that is brisk for a pure classical bulge, and the velocity dispersion pattern is not as centrally peaked as a purely hot spheroid would demand. In several cuts across the center, the rotation remains nearly cylindrical, meaning that stars at different heights above the plane rotate with similar speeds, and such cylindrical rotation is a well-known sign of a bar viewed at an angle. The shapes of the line-of-sight velocity distributions also carry subtle asymmetries that match the expected imprint of bar orbits that pile up near resonances, while gas kinematics trace shocks and streaming along lanes that offset slightly from the stellar major axis, another hallmark of a bar-driven flow. Yet the evidence is not final because dust lanes that cut across the inner disk hide parts of the light, and bias isophote shapes the bulge itself can look boxy if it grew from a stirred early disk, and projection effects in a galaxy that is tilted strongly to our line of sight can blend signatures from multiple structures into one. To separate these layers, observers fit the central light with combinations of a spheroidal bulge, an exponential inner disk, and a bar-shaped component that follows the elongated profile seen in barred galaxies. When the fit includes a bar whose major axis sits a little askew from the disk major axis, the residuals in the light map shrink, and the boxy outlines relax, and the same bar length and angle can often reproduce the kinematic twists, the streaming pattern of the gas, and the mild asymmetry in dust lanes that outline inner shocks. Within this framework, the bulge itself looks old and metal-rich on average, with many stars older than 10 billion years, and with heavy element ratios that recall rapid early star formation. Still, a fraction of stars closer to the plane show slightly younger ages and higher metallicities that suggest some continued growth fueled by gas that flowed inward along the bar and formed stars in the central kiloparsec long after the first epoch closed. The spatial distribution of these younger, richer stars is not uniform. They tend to concentrate in oval zones that align with possible inner rings, and such rings are common outcomes when gas driven by a bar stalls at resonances where orbital families change. Thus, the debate about the bar is not only about shape, but also about process, because a bar would help explain how gas reached the inner few hundred parsecs to build such concentrated younger populations without erasing the broader old spheroid that still dominates the mass. Vertical structure adds another dimension to the argument. In many barred galaxies, the inner light looks boxy or even peanut-shaped when seen at a slant, because the bar thickens through vertical buckling. In Andromeda, the central isophotes show a mild boxiness that grows with height above the plane, consistent with a bar that is not extremely strong, but that still thickens the inner light. Along the minor axis, star counts and surface brightness do not fall as fast as a perfect spheroid would predict, and this mismatch can be modelled by a thick bar that lends extra light at intermediate heights. The pattern speeds that theory allows for a bar in a galaxy, with Andromeda's rotation curve, place inner resonances at radii that match the observed positions of certain dust rings and gas lanes, strengthening the case. Yet models with a triaxial bulge, meaning a spheroid that is not perfectly round but stretched along three unequal axes, can also reproduce some of these signatures when combined with the tilted disk and heavy dust lanes, and the central symmetry is not broken strongly enough to rule out that possibility. Spectroscopic measurements of stellar populations across the central region complicate the scene in a useful way. The oldest, most metal-rich stars dominate near the core and along the minor axis, implying an early rapid formation that built a dense spheroid. Toward the major axis, and within a few kiloparsecs, indices that track young to intermediate age populations rise slightly, and this rise aligns with the proposed bar major axis, and with the inner dust lane suggesting that stars formed from gas that the bar funneled inward enhance the light in those sectors. In addition, the sodium and magnesium lines which trace details of enrichment history vary with position, in a manner that is easier to explain if radial flows have mixed gas along preferred elongated orbits, rather than only in circular rings. Gas dynamics speak with still more clarity. The ionized gas shows non-circular flows near the center, with velocity contours that twist in a way that is natural for gas responding to a bar potential. Cold gas traced by carbon monoxide aligns along narrow lanes that run inside the stellar dust lanes, and shocks inferred from sudden jumps in line width occur where such lanes meet the inner ring again, a pattern the bar would set. Simulations that seed a bar into a disk with a pre-existing classical bulge and an extended dark halo can match these features when the bar is set at a modest angle to the disk major axis and when its length reaches a few kiloparsecs. However, when the bar is removed and the bulge is made triaxial, the fits to the gas become less natural unless additional asymmetries are added by hand, a trait that leaves the bar hypothesis preferred by many but not universally accepted. The central velocity dispersion profile offers one more clue. A purely classical bulge would present a steep central rise that declines smoothly outward, while a barred system often shows a flatter top with shoulders where orbits crowd. In Andromeda, the dispersion map shows a broad plateau across the inner region, with hints of off-center peaks along the putative bar features that weakly favor a bar embedded in an old spheroid. The alignment of planetary nebula velocities and of compact star cluster orbits also shows a gentle preference for elongated streaming that aligns with the same axis. At the same time, the great mass of the bulge ensures that the bar, if present, does not dominate to the degree seen in late-type spirals. Rather, it acts as a sculptor that carves within a heavy block, shaping gas flows and tilting light slightly, without undoing the deep foundation laid in the first epoch. The bulge and bar debate matters because it changes the reading of how the inner galaxy assembled. A pure classical bulge would point to early violent processes such as rapid collapse, or major mergers followed by long passive evolution. A strong bar would argue for sustained secular evolution, where the disk rearranged itself over billions of years, driving gas inward to build central structures and episodic rings. The present Andromeda likely lives between these ideals, an early massive bulge created in the first few billion years, overlain by a bar of moderate strength that formed from the disk, and later thickened driving inward flows that built inner rings and pockets of younger stars. Dust and projection hide and confuse, yet the combined weight of photometry kinematics and gas flows leans toward this layered interpretation. As the narrative narrows further in the next step, the focus shifts from the broad bulge and its possible bar to the crowded nuclear star cluster, where star formation histories become more episodic and where orbits fold into tight nests around the central mass. But even there, the imprint of the bar, if real, continues to matter, because it sets how fuel reaches the core and how the rhythms of the inner galaxy keep time over long quiet ages. At the very center of the Andromeda galaxy, the starlight tightens into a compact nuclear cluster that looks at first glance like a single bright knot, yet closer views reveal layered structure, subtler symmetries, and a rotation pattern that speaks of long, episodic growth fed by inward flows along the inner lanes. The cluster is small on the scale of the galaxy, but enormous when held against human sense, measuring only a few light-years across in its brightest core, and a few tens of light-years when the fainter envelope is included. Within this tiny city, stars pack together at densities that rise far above those in the surrounding bulge, and their combined gravity shapes orbits into nested families that circulate around a central mass while slowly exchanging energy with one another. The light is not uniform. It shows a slightly off-center peak and an elongated inner ridge, as if the cluster were a lopsided ring wrapped tightly around the core. This pattern can be understood if stars follow eccentric paths that align their closest approaches on one side, making that side shine more strongly, even though the mass is distributed nearly symmetrically. Such an arrangement can persist for long periods when held by the deep potential at the center, and when the supply of new stars arrives in bursts rather than as a steady drizzle. Spectra taken across the nuclear region show a mix of ages. The dominant population is old and metal-rich, a continuation of the inner bulge that formed early yet sprinkled among these elders are cohorts of younger stars whose light leans bluer and whose absorption lines show the fresh imprint of more recent chemical mixing. These younger groups tend to gather in rings or arcs, a few light years from the centre, suggesting that gas driven inward along the dust lanes stalled where orbital families change and settled into a compact rotating disk that then fragmented to make stars. When the gas was used up or heated by feedback, starbirth paused, leaving behind a ring of specific age. Later, another inflow repeated the cycle. In this way, the nuclear cluster builds layer by layer, each layer marked by a slight difference in age and composition, and each layer carrying angular momentum set by the direction of inflow at the time. The whole structure therefore rotates with speeds that can reach dozens to a few hundreds of kilometers per second near the very center, and the rotation remains coherent enough that maps of line-of-sight speed draw a small spinning wheel whose axis aligns roughly with the large-scale disk but is not perfectly matched, a tilt that records the fact that inflow does not always follow the same lane. Variable stars add clocks to this scene. The nuclear region hosts compact pulsators whose regular brightening and dimming help fix distances and trace the distribution of old populations, while longer period variables and evolved giants map out slightly younger groups. In a few crowded pockets, very young stars still wrapped in dust announce themselves only in the infrared hiding, where recent inflow left cold clouds dense enough to resist immediate clearing. Between episodes, feedback from massive stars stirs and heats, the local gas-carving small cavities that then cool and collapse or are refilled by the next inward stream. Gas kinematics reinforce this episodic picture. Ionized gas lines split and broaden near the center, a sign of shocks where inflowing lanes meet an inner ring and must change course, and molecular lines trace a rotating structure whose radius is only a handful of light years, a disk that seems to be the present staging ground for future starbirth when conditions permit. The dust that marks these inner flows is fine and patchy, and its silhouettes twist in a tight spiral that often leads the velocity field by a small angle as expected, when shocks push gas slightly ahead of the stellar pattern. Each burst of star formation leaves long-lived traces. Compact clusters with high central densities survive among the older stars, and their motions show that they orbit within the potential well of the nuclear region, while slowly losing energy to the sea of field stars. A few clusters may sink inward over many hundreds of millions of years, through dynamical friction dissolving into the core and adding to the central light. X-ray sources and radio knots, though faint, pepper the region, and betray compact remnants left by earlier generations, their distribution following the high stellar density like embers in a banked fire. The dynamical temperature of the cluster measured by the spread in stellar speeds is high, and this heat shapes the fate of tight binaries and of light clusters that wander too close to the center. In such an environment, close encounters are not rare on cosmic timescales, and these encounters can harden binaries, eject light stars to slightly larger radii, and gradually round the distribution even when inflow arrives in a tilted plane. Yet the rotation and the elongated light show that relaxation is not complete. The cluster still remembers the direction of the latest strong inflows, and the eccentric alignment of inner orbits remains visible. Chemistry adds a quiet layer of detail. The heaviest elements are most abundant near the center, and fall gently with radius across the nuclear cluster, while ratios that track rapid enrichment by massive stars differ from those that trace slower contributions by low-mass stars, a pattern that suggests that bursts have been short and intense, followed by long lulls in which slower processes adjusted the blend. This chemical stratification matches a growth path where gas is driven inward, quickly forms stars on tight orbits, and then is swept clear or heated until the next delivery. The nuclear environment is also shaped by the gravitational pull of the central mass that sits deeper still, a subject reserved for the next section. Even without naming that object, its influence can be read in the rising rotation curve at the smallest radii, and in the way stellar speeds increase toward the core more rapidly than the starlight alone would require. Orbits become more nearly Keplerian in the inner few light years, and the alignment of eccentric paths that makes the lopsided ridge is stabilized by the central pull, which keeps pericenters gathered on one side rather than processing freely. The interaction between the cluster and the broader bulge continues through bars and rings that thread outward. If a bar is present, it can feed gas into the nuclear region, along dust lanes that meet the center with the small offset. If not, oval distortions and spiral shocks can still carry material inward in a more axisymmetric way. Either route produces the same local effect. Gas is delivered in packets, not as a continuous stream, and the packets build stars in rings whose ages can be read. The present light of the cluster therefore acts as a diary of arrivals. In some galaxies, nuclear clusters align tightly with the main disk. In Andromeda, the slight tilt and the eccentric pattern argue for a more individual history, one in which each episode wrote in a hand that is similar but not identical to the last. The nuclear star cluster also forms a boundary in the balance between ordered rotation and random motion. Outside in the bulge, orbits lean toward a hot pressure-supported mix. Inside in the smallest ring rotation gains, then yields again as the central mass takes command. This transition governs how gas can cross the last few light years. In some phases, the cluster's rotating disk acts as a barrier that holds gas until turbulent shocks or stellar winds open small channels through which material can drift inward a little farther. In other phases, a lull in star formation and a softening of feedback allow a smoother inflow. Over billions of years, these alternating conditions likely produced a sequence of quiet star formation events, each leaving a ring, each shifting the balance of light by a small percent, and each adding to the dense heart that now rules the immediate neighborhood. The nuclear cluster, then, is not a mere decoration at the center of a grand spiral. It is the living archive of how inflow is captured, how angular momentum is redistributed, and how the deepest potential well of the galaxy receives and processes material from the larger disk. It rotates, it breathes in, bursts, it remembers directions in light and motion, and it holds within its crowded few light years the seeds of future episodes that will write new layers onto an already intricate core. In the following section, the focus tightens by one more step to the central mass itself, and to the faint signs of activity that glow around it, for the cluster that circles here has grown in the shadow of that object, and continues to set the pace at which the deeper center can be fed. Deep inside the nuclear star cluster of the Andromeda Galaxy, gravity tightens into a single commanding presence, a dark central mass of roughly 100 million, to a little more than 100 million times the mass of the Sun, that sets the pace for every orbit within a few light years, and that quietly shapes the long memory of the core. Stars in the innermost arc move on paths whose speeds rise as distance shrinks with the highest measured velocities, reaching hundreds of kilometers per second, a curve that climbs more steeply than the starlight alone would allow, and that therefore signals an additional compact mass concentrated at the very center. The distribution of light in the nuclear region shows a lopsided brightness with two close peaks that at first seem like twin clusters, yet the kinematics reveal that these peaks can be the bright ends of a single, eccentric stellar disk, whose orbits are aligned so that many stars crowd near the same side of their paths. Such an eccentric configuration remains stable for long intervals when a central point-like mass controls precession and the observed rotation and dispersion maps match the expectation of stars moving within a deep, nearly Keplerian potential very close to the core. Against this gravitational quiet, the signs of present activity are faint. Across radio-infrared and X-ray bands, the central source glows at a level far below that of luminous active nuclei in distant galaxies, appearing instead as a low, steady ember, with occasional small flares. This subdued state implies that only a trickle of gas presently reaches the last gravitational step, where it would heat and radiate strongly before falling inward. The surrounding nuclear star cluster explains much of this restraint. Winds from old evolved stars and from the remains of past bursts fill the region with hot gas, whose sound speed is high and whose density is low, conditions that reduce the fraction of material able to cool and sink. At the same time, the angular momentum of inflowing clouds forms rotating structures that stall at small radii and fragment into stars before they can feed the very centre efficiently. What gas does approach may settle into a thin, hot and inefficient accretion flow in which most energy remains trapped and is carried inward rather than radiated, further dimming the core. The result is a central engine that is present beyond reasonable doubt, yet runs at a tiny fraction of the level at which radiation pressure would balance gravity, a regime that prefers quiet persistence over loud outbursts. Even so, the engine leaves a signature. In the immediate vicinity of the mass, weak radio knots shift subtly over years, and a compact X-ray point sits within the lopsided starlight. Spectra of ionized gas reveal line widths and small velocity offsets near the core that suggest shocks and high temperatures precisely where inflowing lanes must change course to join the very small inner disk. Occasional brightenings on short timescales hint that clumps sometimes cross a threshold and feed the centre in brief sips, after which the local medium settles again into its long lull. Over longer times, the presence of the central mass sculpts the architecture of the cluster. It prevents the eccentric disk from smearing out, fixes the alignment of pericenters on one side, and sets the inner boundary where stellar orbits become tight and nearly closed. It also influences how compact star clusters migrate. Those that sink inward through dynamical friction dissolve into the cusp of stars bound most strongly to the core, adding light and mass, while slightly changing the velocity distribution. Encounters between stars become more energetic near the centre, and the population of stellar remnants grows, as shown by faint X-ray sources sprinkled through the inner few light years. All these slow processes feed back on the availability of gas. When a burst of star formation occurs in the inner ring, winds and supernova explosions heat and drive away much of the cold material that might otherwise have drifted inward, postponing the next phase of feeding. As the hot gas cools and mixes with fresh delivery along the bar or the inner spirals, a new episode may begin sending a little more matter toward the core. The timescale for this cycle is long on human terms and moderate on galactic terms, measured in tens to hundreds of millions of years, and the present quietly glowing state likely sits somewhere along this repeating curve. The gravity of the central mass also affects the structure of the broader bulge. Orbits that pass near the centre are deflected and can be scattered into thicker, more vertically extended families, shaping the inner light into a subtly boxy or peanut form when viewed at a slant. If a bar is present, its inner resonances define where gas rings accumulate, and the central mass helps set those resonant radii by deepening the potential and altering pattern speeds. In this way, the dark core participates in the choreography of rings and lanes, even when it emits almost no light. The faintness of present activity invites comparisons. Many galaxies of similar size carry central masses of similar scale, yet their cores range from brilliant to nearly silent. The differences often track the supply and the angular momentum of gas delivered from kiloparsec scales to parsec scales, the efficiency with which that gas sheds heat, and the recent history of star formation that either clears a path or blocks it. In Andromeda, everything points to an engine that is well supplied with gravity but sparsely supplied with cold fuel. The halo is massive, the bulge is heavy, the nuclear star cluster is dense and inward lanes exist, but each layer imposes filters that allow only modest intermittent feeding. That intermittence may be a lasting pattern. As the Andromeda Galaxy and the Milky Way move toward one another, over the next few billion years, tides during the first close passage will rearrange gas on large scales, drive shocks, and ignite star formation in wide arcs. Some of that gas may find its way inward along freshly established bars and spirals, fighting past hot halos and turbulence to reach the inner rings. If so, the central mass could brighten for a time, and the nuclear cluster could record another layer of recent stars with ages that line up with the timing of the encounter. Yet even in that active phase, the deep potential of two merging halos and the rapid heating of much of the gas will limit how long and how strongly the core can shine. The central mass therefore appears set to remain a quiet governor, rather than a roaring engine, a presence that curates the structure of the heart more than it announces itself to the wider sky. Measurement continues to refine this picture. Better astrometry of stars very near the centre tightens the mass estimate and tests whether any extended dark component shares the inner region. Improved spectroscopy over very small scales reads the line profiles of ionized and molecular gas, where the last torques act separating rotation from turbulence and shocks. Higher resolution radio and X-ray imaging maps the immediate environment of the mass, searching for jets or outflows that might be present at levels too subtle to dominate, but strong enough to carry energy back into the cluster. Those searches will likely find complexity without theatrical display because everything else in Andromeda argues for a balanced core that breathes quietly. The central mass is part of the memory system of the galaxy. It remembers the sum of all inward flows in the way it has grown. It remembers the orientation of arrival in the tilt and eccentricity of the nuclear disk. It remembers pauses in the age gaps between rings. It remembers close passages in slight changes to the inner dispersion field. This memory is not written in a single file, but in overlapping layers that can be read with patience, and each layer is held in order by the gravity of the mass itself. As the narrative prepares to close the journey inward, the scene is one of controlled power. A heavy compact object sits at the focus, spun about by a cluster that formed in episodes fed by lanes that thread outward through a bulge shaped by long histories and wrapped by a disk whose arms and dust and rings all carry the stories of growth and approach. The core glows faintly today, likely to glow more in a future tide, and always to weigh on the orbits near it with a steady hand that neither hastens nor relents. It is the still centre around which the entire galaxy turns in lore, and in memory, a quiet heart whose rhythm is gravity itself. The timeline of encounter between the Andromeda Galaxy and the Milky Way unfolds across spans that dwarf human history, yet move with a clarity that steady measurements make tangible a sequence that begins with overlapping halos and ends with a single larger galaxy, whose light and motions carry the layered memory of both parents. In the present age, the dark matter envelopes already press softly into one another, trading gentle tugs that slightly reshape the outer orbits of satellites and lengthen some streams, while the hot circumgalactic media mingle along a broad border where thin shocks and compressions slowly raise the temperature and mix heavy elements shed by many generations of stars. Over the next few billion years, the separation narrows, and in roughly 4 to 5 billion years the first close passage arrives not as a sudden collision of stars, but as a deep tide that pulls on disks, rings and bars, drives gas into arcs and bridges, and scatters some stars outward into long tails that fade into the shared envelope. The approach speed is only a few hundred kilometers per second, modest in cosmic terms, and the sideways drift is small but not zero, so the track of the first pass likely misses a perfect center, by a little sending one disk through the outer parts of the other at an angle that decides which spiral arms feel the earliest rise in tides, and which regions light with star formation first. Gas clouds meeting along bridges are shocked and compressed. In the wake of those shocks, clusters ignite, and for a brief era the outer disks wear chains of blue star-forming knots that brighten, drift, and fade. The inner bars respond by funneling gas inward feeding rings that glow near inner resonances. The central masses so quiet today may flicker as fresh fuel reaches the inner few light years, and the nuclear star clusters may record new thin rings whose ages align with this first passage. After closest approach, the galaxies swing apart into a wide arc. Friction within the halos, the exchange of energy between dark matter and stars, and the pull of long, tidal arms slow the motion. Over perhaps 1 to 2 billion years, a second passage follows closer than the first, and then a third, each pass shorter and deeper than the last, with tails and shells piling material into the common envelope. During these phases, some satellites change allegiance, captured by the other giant or cast onto wide orbits that later fall back. Streams that once traced the separate halos are bent into new shapes that no longer remember a single parent, and globular clusters are scattered onto orbits that reach across the entire system, marking the growing remnant with hundreds of bright old beacons. Gas physics decides how dramatic the middle acts appear. If enough cold gas remains after the first rush, the second pass can drive a new wave of star formation, though the hot shocked medium and the deepening potential will tend to heat and stabilize much of the remaining supply, so bursts come in pockets, rather than in a single global blaze. Dust lanes are torn and reformed rings are stretched, and the bright arms that once held ordered sequences of birth become patchworks of younger and older regions. Yet through all of this, most stars never hit one another. Space is too wide on stellar scales. Their paths change because of tides, not direct collisions. The solar system, carried on its patient orbit around the Milky Way, feels the evolving global tide but remains bound to the larger system. And while the sky would one day show the stretched form of Andromeda grown enormous, the local gravity of the Sun remains the decisive hand for the planets. As the passes continue, the two central masses spiral toward one another within the merging nuclear regions. When they finally coalesce, they send out a pulse of gravitational waves that ripples the fabric of space itself, a giant but brief whisper that, if watched by a distant and sensitive listener, would mark the unambiguous union of cause. The merged central mass grows by the sum of both progenitors, and a faint burst of activity may follow if gas is ready to hand, shining across radio-infrared and X-ray bands before settling again to a low, steady glow. The final remnant takes on the form of a large elliptical or lenticular galaxy with a deep extended envelope. The rotation of the original disks remains in the orbits of many stars but is scrambled by the repeated tides into a broader, hotter distribution, where random motion carries as much weight as coherent spin. Shells and ripples linger for billions of years as the last phase mixing proceeds. Faint carvings that fade slowly into a smooth light. The dark halo becomes a single massive well, whose shape is rounder at large radii with mild triaxiality inwards, where the memory of the merger survives in the orbits. Globular clusters settle into a rich extended system, with multiple subpopulations, some more metal-rich and centrally concentrated, others more metal-poor and scattered widely, fossils of the two original families and of the many dwarfs that fed both. The intergalactic medium of the former local group becomes the inner atmosphere of the remnant, hotter and more enriched than before, threaded by the faint remains of bridges that once connected companions. Some satellites survive the union and orbit the remnant on wide paths, others are shredded into streams that wrap many times before dissolving. The total light of the remnant grows redder as short-lived blue stars from the star-forming intervals die, leaving a population dominated by older, cooler stars. In this future, the name local group loses its meaning because the two great anchors are now one system, and most of the smaller towns have been absorbed or placed on paths that belong to the common city rather than to any separate part. The night sky seen from within the remnant would show a diffuse elongated glow where once a barred spiral stood, and around it a wide halo with a rich wreath of clusters. The timeline of these changes is not a sharp schedule, but a range set by mass, by the small sideways drift at the start, and by how much gas remains to cool between passes, yet the broad bookends are secure a first close pass in roughly 4 to 5 billion years, a settling into one body in roughly 6 to 7 billion years, and long after that a quiet, slowly evolving remnant that brightens only in small places where a cloud cools or where a cluster passes close to the core and is stripped into light. The lessons carried into that remnant will be many. The coherence of long cold streams today will become the wide, smooth halo of tomorrow. The warp that now lifts one side of the disk will become a memory in the faint shells of the remnant. The central masses that now breathe quietly will merge and then return to quiet. The spiral arms that now host ordered birth will become fossil orbits in a sea of stars. The heavy elements made in each galaxy will be shared across the new system, writing a blended gradient that passes gently from center to edge. In all of this there is no final verdict about beginnings or ends, only a change of shape and rhythm. Gravity gathers, stirs and rests, newborn stars blaze and fade, streams unspool and vanish, halos overlap and become one. The timeline of encounter is not a catastrophe, but a long exchange, a slow folding of two grand patterns into a wider, calmer whole. When the narrative of the Andromeda Galaxy and the Milky Way is read far in the future from within that remnant, the pages will show that every feature described along the path inward had a part to play, the halo that set the pull, the streams that marked the routes of past arrivals, the companions that set talks, the warped edge that told of older nudges, the arms and dust that paced starbirth, the bulge and bar that carried gas inward, the nuclear cluster that recorded bursts, and the central masses that governed the last steps. The encounter is therefore not an interruption, but a continuation. The next chapter in a book the universe has been writing since the first ripples in the ancient background became the web along which galaxies flow.